Welcome back to this NPTEL online certification course in molecular rearrangement and the reactive intermediates. In the last class, I started talking about the Grignard reagent. I talk about the generation of Grignard reagent, the effect of solvent, and the radical mechanism for the generation of Grignard reagent. In the today's class, I am going to talk about the different type of mechanism using the Grignard reagent. So we are going to start with the reaction with the carbonyl system. And then of course there will be reaction with a enone, so there will be a chance of 1,4 versus 1,2 addition. We are going to talk about the stereochemistry and some of the cross coupling reaction also done with the Grignard reagent. So let's start about this. We are going to talk about first thing is the addition of the Grignard reagent to the carbonyl compound. I think in the last class I started talking about that, and I think I talk about that. You see that there is going to form a tangent state which is a 6 member, and we also talk about that this magnesium going to activate this, one of this magnesium going to activate this oxygen of this carbonyl group. And if you think about this is having R, we also wrote about that there is a magnesium, then there is another R, and you can think about a tangent state like this. So there will be a 6 member, so if you think about 1, 2, 3, 4, 5 and 6. So these are involved and forming a tangent state. That's what we informed you in the last class. So one of the magnesium, what is happening here, this is acting as a Lewis acid to activate this carbonyl group, so that the another magnesium can actually this can attack to the carbonyl group. Okay, again I think you can see if you have bulkier Grignard reagent, then it can happen here. It can also, you can write something like this, that here the single magnesium can also activate this oxygen here in the carbonyl, and this R group can attack here to form this OMGX. From there it can go to the corresponding alcohol. Now you can think about there are different type of carbonyl group, means it can be a ketone, it could be ester, it could be amide, and the reactivity rate is aldehyde will be react faster, then ketone, then ester, then amide. Okay. So now we are going to learn that the Grignard reagent not always going to react with the carbonyl compound. So there are two other possibility can happen. The second possibility can happen if it is really bulky that it cannot add for 1,2 addition, then it can go for a formation of enol. That means it can act as a base. So in the previous slide I talk about that it can act as a nucleophile, go for 1,2 addition. Now it can act as a base to abstract this proton here to form a enol, which can be protonated to form this corresponding carbonyl compound. It is going back to the corresponding carbonyl compound. Or if you can treat with some if you can take some electrophile, then there will be electrophile going to come. So what is happening here? So here it is acting as a base. Now there is another important thing here, there is a hydride transfer, that is another important parameter. So using, I think you must have heard about hydride transfer, like if you use sodium borohydride, remember, to reduction of the carbonyl compound. So here we also found that in case of some Grignard reagent, okay, where instead of going for 1,2 addition, if you cannot go for 1,2 addition, and if it is don't have this type of proton of the alpha to the carbonyl group to abstraction, means if the enolization is stopped, then this is the last thing it can do. What it can do, it can go for a hydride transfer. You can think about this minus can come back here, and then this hydride can transfer to the carbonyl group, and what it will end up making, from the carbonyl group to it will go for a reduction reaction happen to convert to the corresponding alcohol. Okay. So what you have learned, that depending on the Grignard reagent there will be 3 scenarios. One is a 1,2 addition, that means Grignard is acting as a nucleophile. It could be go for a enolization if you have a bulky Grignard reagent. So here it is acting as a base to abstract the proton, alpha proton, the carbonyl group. Or if you have a scenario where it cannot go for 1,2 addition and it cannot go for enolization, then it can go for this hydride transfer to reduce the carbonyl group to the corresponding alcohol. So here is an example I am trying to show you. You will be convinced with this data that if you start with this corresponding ketone and now you treat with the Grignard reagent first with CH3MgX, you see 95% of 1,2 addition, means once you think about a CH3 MgX is reacting, it is actually adding to the carbonyl group to form the corresponding product, which is once you treat with the H3O plus, this is going to form the OH with the CH3. So this will be your 1,2 product. Now what is happening, once you go for a tertiary, so what is happening here, you are seeing 35% enolization and 65% reduction happening. So what is happening here, again you can see here in these cases, once you have this bulky Grignard, and you can see this ketone is also bulkier, so there is this proton, this proton can be absorbed easily by this, so it can act as a base. Okay, to absorb this proton, this will go to the forming a enol. Okay, and then also you can see it can also go for a reduction. As you can see, both the Grignard and this one is bulkier. Sometimes the enolization is not that not that favorable. So instead of that, what is going to happen? You can think about this methyl as having 3 hydrogen. So it can go for this type of reaction. It can form isoprene, and it can attack to this hydride can attack to the corresponding carbon compound to form a corresponding alcohol. So this is your reduction product. So you are seeing a mixture of enolization and reduction. Now if you use a Grignard reagent, let's write this one, the structure of this. So you can think about, this is the structure, you have a CH3, 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 then CH2, then MgX. So if you think about this Grignard reagent, what is the importance of this Grignard reagent? There is no proton here. We replace, there is 3 CH3 group here. As you see, there is, you need a beta proton to be, for this, the hydride transfer to be happen. But there is no beta proton here. So that's why one thing is happening, this can only participate in enolization. That's why you can see 90% enolization happening with this, but there is 0 reduction. Again, magnesium is not so hard with the, similar to lithium. It is not that soft like a copper. It can in between. And again, you can still think that once you have this type of alpha beta unsaturated ketone, like aldehyde especially, then as the aldehyde is very reactive, the Grignard will go for the 1,2 addition only, majorly. But once you have the ketone, as I said, the ketone reactivity is less compared to aldehyde, you will see the major is this 1,2 addition, and at the same time you will see some 1,4 addition going to happen as well. So here is an example again given here. If you start with this particular enone, and once you try to change the Grignard reagent, for this particular one, what we are seeing here, majorly this the 1,2 addition happening, and then you will see some amount of 1,4 addition. Again, this type of alkyl Grignard reagent, we are seeing this primary alkyl Grignard. What we are seeing here, we are seeing the formation of this 1,2 addition as a major product. Once you started going to the secondary one, what you are seeing, this 1,4 addition product is getting increased, and then in the tertiary. Of course, in the tertiary there is other things going to happen. Of course, there is one thing going to happen. It can give you some product of enolization, and the some product of the hydride transfer also going to come out. So, but the thing is, now the question arises, can you find a method where the Grignard reagent can only go for 1,4 addition? Is it possible? Yes, you can do it. That then you have to use some copper catalyst. We are going to come back to that. So you can convert this Grignard reagent to organocopper reagent, and then it can go to participate only for because it is a softer one, it is going to participate in a 1,4 addition instead of the 1,2 addition. So we are going to discuss this in more detail in the organocopper chemistry. Now if you treat with the formaldehyde here, it is going to form this corresponding 1 degree alcohol after the Grignard addition, and then quench with the H3O plus. If you have a acetaldehyde, it will go to the secondary alcohol, and if you have a ketone, it will form the tertiary alcohol. So depending on if you want a primary alcohol, you have to go for formaldehyde, secondary alcohol acetaldehyde, and tertiary alcohol, then you have to go for the corresponding carbon compounds. Now if you have a ethyl formate, what is going to happen? So now we are talking about reaction of Grignard reagent with a ester. Of course, the first reaction going to happen once it will form this intermediate. This is going to get out. It is going to act as a leaving group. Okay, so to form this corresponding acetaldehyde. Now the question is, does the reaction will stop here? This reaction will not stop here. Why? Because you formed a more reactive compound. In the product you have generated, if you think, sir, I will use one equivalent of Grignard and I can get one equivalent of product. No, you cannot, because as soon as your Grignard started reacting with ethyl formate and it starts generating the corresponding acetaldehyde, now the Grignard is going to choose acetaldehyde more compared to ethyl formate, because acetaldehyde is much more reactive compared to this ethyl formate, because this is the aldehyde, that's the ester. That's why the Grignard will react again with this to take you to all the way to forming a secondary alcohol. That means if you want to make a secondary alcohol, you don't have to start with acetaldehyde, you can start with the corresponding ethyl formate as well. Again, you have to remember, in this ester reaction you have to, I think it's better if you want to get to the 100% of this product, what you understood, that a 2 equivalent of Grignard reagent actually added, correct? So 2 equivalent as Grignard reagent is adding here, so that's why in the reaction also you should add little more than 2 equivalent for a complete conversion. Again, if you start with the corresponding acetyl chloride, the first thing is it is going to attack here. Now chlorine is a good leaving group, it is going to form the corresponding acetone from this acetyl chloride. Now again the acetyl, the acetone is more reactive than corresponding acetyl chloride, so Grignard will not going to stop here, it is going to add here to take you all the way to the corresponding tertiary alcohol. If you have a carbon dioxide, I think very similar to the organolithium, it is going to react with the carbon dioxide, it is going to add to the carbon. Then once you treat with the H3O plus, it is going to form the corresponding carboxylic acid. Okay. Again, you might be thinking, sir, is it the reaction why it is stopping in the carboxylic acid? Again, once you have a carboxylic acid, then the Grignard can abstract this acidic proton, correct? Once the Grignard is abstracting the acidic proton, then it cannot attack to the corresponding carbon group. Here it can attack to the epoxide, okay, it can attack to the epoxide, and epoxide can form the OMGI, which will treat with the H3O plus, protonated water can form the corresponding primary alcohol. Very similar to the organolithium, it can attack to the corresponding acetonitrile or corresponding the cyanide. It is going to form this corresponding imine, and then the imine is going to hydrolyze to form corresponding ketone. Okay. Again, I think in this reaction, once it is forming the corresponding imine, I think it is going to stay here in the imine, because what is going to happen here, after the formation of the imine, the Grignard has one thing, Grignard can act to the corresponding imine, because I think this can happen after the workup, correct? Once you have a imine and if you go for workup, you will get only this, so then this is not going to happen, correct? But I think in this particular cases also, what people found out, that in some cases if you have some moisture, if you have some stress of moisture, and if some ketone is started forming, then that is going to also get reacted. Otherwise you can convert this to corresponding ketone at the end. Now the question comes then, is there any other way to solve this problem? So what we stuck with the problem that if you use this type of compound, that if you use this acid chloride or if you use this ester, what we are seeing there, we are majorly seeing that reaction is going all the way to the corresponding tertiary alcohol, means 2 equivalent of Grignard is attacking. How to stop it? For that it was developed, the winner amide was synthesized. So this is a very clever approach. You are going to learn in a minute why that is very important and why you have to synthesize this particular amide. So here I think the synthesis is very easy. You can take this particular amine, and then once you react with the corresponding or you can have this corresponding N, there will be a nitrogen here. Once you have this N MgClO, with this type of Grignard reagent, if you treat with the ester, or in these cases if you treat with the corresponding acid chloride, then what is going to happen? It is going to form this corresponding winner amide here. Okay. So now once you form the winner amide, and now once you treat this one to the corresponding organolithium or corresponding Grignard reagent, what is happening here? Once you treat them with the corresponding organolithium or corresponding Grignard reagent, we found out after the reaction is happened, once you do workup, every cases we end up getting this ketone as a product. We isolate this as a product. So what is happening here? You might be asking this question, sir, if this is attacking in the reaction, and if it is forming this ketone in the reaction, then why this Grignard is stopping there? Why it is not attacking to the ketone? So the thing is, it is not that simple here, because you can think about that once this reaction is happening. I think I can try to show you that once this reaction is attacking to this R minus RMGX, you can write, or RLI. When this is attacking to the winner amide forming this O minus, now if you try to think about the corresponding tangent state here, because this in this reaction it is not forming a ketone, it is actually staying in this form, and here this O methyl is playing a very important role. This NO, everything is playing a very important role here, because once the attack is happening by the Grignard reagent, then this metal could be a magnesium or could be a lithium forming a chelate with the oxygen. So in the reaction it is staying in this chelate form. So you have this one plus extra RMGX or RLI in the reaction. So these are lying in the reaction extra. So now if you quench the reaction, this is now in the, after you put H3O plus only, then only it is going to convert to the corresponding ketone. So till then it is in this form. So that's why it is not getting attacked. Okay. Because, and then your extra Grignard is getting quenched also once you treat with the H3O plus, that can convert to RH. Okay. That is the important tricks here. Again, the Grignard, if you have any water, or if you are synthesizing this Grignard, if you are careless, then the Grignard is getting quenched here. If you have the Grignard getting quenched to alkane. So you have to be very careful when you are making Grignard. You should make sure your glassware is completely dry. Then Grignard reagent can be participated in alkylation. So we have learned about the Grignard reagent is only doing some reaction with the carbonyl compound, with epoxide, with ester. It can also react with heteroatom. It can react with phosphorus. Okay. It can react with the tributyl tin chloride, with BF3 ferrite. It can also react. It can also react with trimethoxyboron to form the boronic esters, or corresponding tin compound, corresponding phosphorus compound. So Grignard Grignard reagent has a lot of importance to form the the heteroatom bonds as well. The other important question is, if you think about the addition of Grignard to a carbonyl group, then it can add to the above phase. As you guys remember, the carbonyl group has a C and the Re phase, so it can attack to either of the phase. So that means what is going to happen if you take a Grignard reagent, and if you have a R and R1 is a R1 R2 is a different group, you end up forming a racemic mixture. Okay. So here the question comes, if you have a scenario here, you have a chiral center and you have now you have aldehyde, and now you are shooting with a Grignard reagent. So the question comes, which of them will be major? Is it going to be this one going to be the major RR isomer, or the RS isomer going to be major? That means now which phase of this carbonyl group the ethyl group going to be approached. So to explain that, you have to try to understand the Cram's rule and the Cram's model. I think it was clear from this model that whatever groups will be present, it is so the nucleophile always going to attack from the less hindered side. That means if you can think about, there will be the groups can be numbered with a medium size, small size and large size. Okay. So nucleophile will always try to approach from a less hindered site. So this will be the less hindered site between this where the nucleophile can attack. Once that is happening, you end up getting to a stereoselective product here. And now the question comes, if you have in your compound where you have the carbonyl group going to get attacked, but you have a O-methoxy group, what that can act? That can form a chelation. Now you know the Grignard is going to form a chelation with the oxygen. We have already learned about that. And now this O-methoxy group is also form chelation. So that can also going to favor the chelate tangent state. So now you can see this it is not going to follow now the Cram's rule original hypothesis. Now this chelation going to be drive the reaction towards product. Okay. So because of the chelation, now the nucleophile going to attack from this side to form this product as a major product. So we have learned about the carbonyl addition. Now we are going to learn about some cross coupling reaction. So it was discovered a lot early that if you take a Grignard reagent, like if you take a aryl Grignard reagent, ARMGX, and if you treat with the iron catalyst, PCl2, then what is going to happen? It was known that it is going to convert to a biaryl, and not only iron, there are a lot of other catalysts was developed which can convert the Grignard to the biaryl. But now I am going to talk about if you have a alkyl magnesium halides, or you have aryl magnesium halide and you have a aryl halides. Okay. So now this thing can be coupled using depending on if you have aryl versus alkyl, then you can use palladium or the nickel catalyst once you have alkyl, and then using a ligand you can able to go to the corresponding, again it can form a biaryl if you have a 2 aryl group here, or it can form a substituted aryl compound. So this is going to introduce you to the Kumada coupling. Okay. It was the first it was discovered with using palladium or using a nickel catalyst reaction. So this is again going to follow the various, I think if you guys heard about in the organometallic chemistry about the Sujui coupling, if you remember, in the Sujui coupling we use the organoboron as a nucleophile partner and the aryl halide as electrophile partner, but here in the Kumada coupling the Grignard agent is used as a nucleophile partner. So mechanistically it will be very similar. Once the palladium 0 catalyst will be generated in the medium, it can go for oxidative addition. Then there will be a transmetallation which is Grignard agent to get rid of this halide. Then there will be cis trans isomerization, and finally reactive elimination to get to the product to get by the palladium 0 in the catalytic cycle. Again, as I mentioned, the iron 3 catalyst or iron 2 catalyst can also use for this type of reaction. Here is an example here. If you start with this corresponding chloride, and if you can use this the iron catalyst, then what can happen? Not only this reaction will work for the corresponding the bromide, you can use this corresponding chloride for the cross coupling as well. So now you can use this Grignard agent here that can participate in a cross coupling to synthesize you this substituted esters, okay, which can be converted to the corresponding benzoic acid derivative. So now I think I am going to show you that so again there are a lot more cross coupling. Again this particular course I am not again so this is not a, we are not going into the lot of the different cross coupling reaction using the Grignard agent. We are just showing you some of them. Okay. And of course if you are taking an organometallic course mostly which are dealing with a cross coupling reaction with palladium, you can see more detailed study there. Here I am going to show you one of the importance of this particular reaction. If you have a Grignard agent like aryl magnesium bromide, here what is happening, you have a carbonyl compound here. So this particular so here the Grignard reaction was used in an industrial production of tamoxifen. So tamoxifen is an anti-cancer drug. Okay. So you can see tamoxifen actually is a tetrasubstituted olefin. You can see this will be the structure of a tamoxifen. You have a phenyl group here, you have ethyl group here, you have a phenyl here, okay. So now you can see this can be synthesized through tamoxifen, but first thing is the Grignard is adding to the corresponding carbonyl compound. So this carbonyl compound was synthesized first. Now the Grignard group is adding to the carbonyl compound to form this corresponding tertiary alcohol. From there, after the dehydration, it can form this corresponding olefin. Okay. So this is the industry scale synthesis of tamoxifen, where the Grignard agent is also utilized. So in this particular segment, I talk about the reaction of Grignard agent with a carbonyl compound. I started with that aldehyde will be much more reactive, then a ketone, then a ester. Also I talk about in case of ester, it is going to form two equivalent of Grignard going to attack to form tertiary alcohol. You can stop this if you can make a Wiener-Bromide, then it can go to the corresponding ketone. And then also I talk about if you have according to the Kram's rule where it will going to attack, it's going to attack to the less hindered side to the carbonyl group. And also I show you the application as well. Okay. Again these are the references you can follow. And again thank you to the coming to the class, and I am going to see you in the next class. In the next class my plan is to talk about the organocopper chemistry. Thank you.